difficult. This is, I'll just write the question. Find infinity pi by 2 cos pi by 4 it and so on till cos pi by okay. So you see, I mean, I'm sure you people can do this problem. It's not a big deal. But before we get into that, I would just want to say that that you should not have problems in interpreting this as a limit of a sequence. Okay, this is the sequence. This is the nth term of the sequence. So let's just solve this. Right, so this I think is a well-known problem. Oh no, probably have to do it the other way. Yeah, just do it the other way. So what is an? So it will be this, right? Just simplifying. Is that what you get? Yes, no. And then this is actually very simple then. And then limit is just 1. Or maybe, yeah. Is it correct? Am I audible?
Yes, yes,
Yes, sir.
one.
Right. So this is a very simple problem. Yeah. So, well, you see so what is the good thing about why does this problem become easy, right? So Vaishnavi, you can work out. If you have not worked out the details, you can just do it later. But the point, yeah, so it's easy. It's just a telescoping product. But the main thing is that this is a product. This is what is called infinite product. Okay, it's a limit of increase. It's a limit of products where there are increasing number of factors, right? And well, it's of the following form, right? An is equal to b1, b2, bn, right? So this limit of an is what we want to find, and this is usually as it should be denoted like this, right? It is denoted like this, and it's a very important question in mathematics in many areas to understand this limit, to understand this limit, and to know when does the limit exist. And maybe we should also say when does the limit exist and not equal to zero. Because for these kind of problems, it's also important to identify if the limit is zero or not, right? Because if the limit is zero, that also you would want to know, because such products. So it could go to infinity, that's one thing, but also going to zero is another kind of thing which you would want to detect, just like going to minus infinity, you want to detect. So, so because of that, even if you look at Apostle's multivariable calculus, I think he has a section on infinite products. But I will want to say a few things on infinite products, and then you should take them as exercises and do it and read about it.
Sir, I guess one thing you can immediately say is that the Bn, it should tend to 1. So if the limit exists,
Yeah.
then Bn will be tending to 1.
Yes, that's a good starting point. That's certainly a necessary condition. Right. Yeah, let's build on that. Let's see. This is an. Then you want to understand limit an. So certainly we have the bn tends to 1. This is just as you know the nth term should go to 0. Here it should go to 1. You can understand. You can take logs. Even for negative numbers, you could take logs if you know the complex logarithm and so on. But if not, then you can just
Or
think, yeah,
so what we can do is we can take limit An plus 1 over An. And if the limit
yeah.
exists, then it'll be, so then limit
Certainly,
Bn will.
certainly, yeah. I mean, the proof is certainly there, yeah. But I'm just saying that it is analogous to it can be reduced to that situation of summation. So that's a thing. But what other conditions can we give? That's really the question. I mean, what sufficient conditions can we give? We are looking for some sufficient conditions. And this is very useful. So the point is that you would want to quantify the intuition that it should go to 1 rather quickly. It should go to 1 uh, as, I mean, yeah, right? Should that's the intuition, right? For the product to be finite, it should go to 1 quickly. So how do you quantify that? So what if I said that summation uh, right. So let's assume for the sake of simplicity that these are all positive. And yeah, I would also want to assume some other things. Let me just assume for the moment that these are all bigger than 1. Okay, fine. So this is just assuming. Okay. Now, uh, sorry, what if I told you that this Bn minus 1, this summation is finite, right? Does that imply that the limit is finite? Can anyone see that quickly? So we have we have gone from product to summation. So that's why you have to think, maybe. Well, so I mean, you have to quickly go from product to sum, and you know the usual things is exponentials and logarithms is what help you to go back and forth, right? E to the power x is a homomorphism uh, from r cross to r plus, right? Those two groups. But I mean, it depends on how you think. If you don't yet think in terms of those groups and rings, you should start doing that. Otherwise, you will never get good. If I learn a language and I don't talk in that language, then I will never learn it. I'll never be able to use it. It's as that's like that. But well, so all that is fine. But what is the main thing? Yeah, is this helpful? This one? No, this is not the way. This is not the way. Because you want to multiply downstairs, that will be addition upstairs. So you have to use this. I think now the proof should be clear, right? Simply based on this thing, which you know. Okay. It took me so long to get here, but should not have. So if you use this, then you just have that this is finite. So this would imply that this is finite. This is finite. So it would imply this is finite. That would imply the product is finite. And it's all greater than one. So everything is a positivity is not a problem. And so then it's, yeah, right. And this bn greater than one also implies that an is increasing. That also you should know, and that is clear. If the what you're multiplying by every step is greater than one, then of course sequences in product will decrease, and yet it is fine. So this is a very small, silly condition in which it works. Okay, not I mean nothing is not some. It's a very general condition which always works, so it cannot be very difficult. Okay, so you should work out the details if you don't follow that. I mean, don't follow. I suppose you follow it, but just that if the details. But you should look at this. Now let's look at the other conditions, or rather, just tell me what should be the other. What should you do if? I mean, I would not bother looking at negative bns maybe for the moment, because that can get that's something which we are not interested in for some reason, right? You can see that. But let's leave that for the time being. So if this is the situation, then what should you? What criteria can you pull up for this case? Again, you just want to ensure that it goes to, right? So of course, in that case, it should be this. Right? I mean, 1 minus b, and what else will it be? Right? I suppose that's completely symmetric. There is nothing to do really. Okay. So please prove these things. So this is if bn is greater than 1, and this is if bn is 1 and 0. These are nice little exercises in analysis. But this is like just for numbers. These are sequences of numbers. Is it fine? Is these criteria are okay? Do they look okay?
Yes, sir.
Right. So these are very simple. I mean, of course, the interesting things I don't know. That's the problem. I mean, there would be many interesting conditions, and so there will be some class of sequences and partial this products for which some interesting criteria will work. But in general, interesting criteria will not work. Right? But those will also be some general enough condition, general enough situation. But what I really wanted to say is not these. Wanted to, and just that's maybe the last thing I will say on this topic, is about yeah, maybe for that I have to look at the book. So let me open the book, show you, or maybe I can try to first do it myself. The only thing is that doing it myself will take some time. So we'll see. Just do it and then I'll look at the book. So please do these things, and because usually it's, but when you do many topics like in analysis, when you do the analysis on like Hilbert spaces or those kind of things, then these are very useful conditions, useful information, where criterias, and then most importantly, when you do complex analysis, it's very useful. Okay, so with that infinite product of functions, okay, and we will, because sequence of functions, so now we would want to understand that. That's, we'll stop there once we do that. So let me use the notation that is more standard. So if you, I'm using Z because I'm thinking of these functions on the complex plane, because that's where infinite products are really useful, at least to my knowledge, because of certain reasons. But so look at these and just think of these FIs as functions. It will not be very important with the domain and range, but say let's say from C to C. Okay, certain interesting things happen. So first of all, what should be the condition, right? Because we are dealing with functions, we'll be safe. We'll just play safe, I should say, and put yeah, like if you think about those two conditions, right, you could have clubbed them into this condition, I suppose, right? I think it will be clear to you people that it's, I mean, at least from a standpoint of guessing, right? Or I should say, I mean, from if you just had to guess, so then if you have this, okay, then I would guess that this would imply that Fn converges, right? Right? Or maybe I should just, I mean, you will quickly see that it's becoming easy because why is it becoming easy? Because if I say this, it really means nothing. We are back to the same situation because for every z, these are numbers. These are complex numbers, but that makes no difference. You can deal with that, right? You can set up the appropriate things and you can deal with that. Because at the end of the day, the conditions are in terms of mod, so you can deal with it. So this statement should be clear. This is nothing to prove. Actually, it's same problem in fact as the previous one. But obviously, you have to if you have not practiced much. Well, if you complain about this, then you can just look at R2 and it's fine. Well, the problem is that at R2 you don't have a multiplication, so maybe you should think about C only. It's up to you that you know what convergence in complex numbers mean. I mean, you can just convergence is same as in R2, only that for the operation you need to go to C to have your familiar operation. Otherwise, yeah. So this you should prove, but this one I will just think and make a guess and we'll check it. That now people know what is uniform convergence and all that, right? So that's why this is important. Yeah, let me first say that if no need to write if. So when I write this, I mean uniform convergence, right? Uniform convergence. So uh, should I explain what I mean by uniform convergence here? No, you have to unpack a lot of things, but when you do it, it's very easy. These are just functions, and this is this convergence of this means convergence of this. Uh, this is a function, and so it's a limit. So uniform convergence. You all know all that Weierstrass M test and so on, right? So you can use those things, but you don't need those things. But I'm saying that's an example where uniform convergence comes. This will be not so. So when we write this, we mean uniform convergence. Okay, so you should try this exercise. Is very nice. This implies that Fn converges uniform. So when I just write Fn, then I mean uniform because it's a convergence of functions. So probably the only convergence that you know for functions, or the most standard one, is uniform convergence. Correct? Okay. So if you want, I will clarify it this, but otherwise I will leave it and I'll go and check if this is correct. So what is a good place to look at that? So there are two books, Stein-Shakarchi Complex Analysis or Rudin Real and Complex Analysis that I can think of. So let me go to Stein and Shakarchi. I have the book.
I guess
Ah,
at least for the case where each Bn is positive, studying the infinite product, it's equivalent to studying the sum of log An.
yeah. That is there, correct. Yeah,
Yeah.
in those cases, the problem is completely in terms of logarithms. But the reason why we usually don't, no, usually we don't write it in terms of log because now you come to this and there is no log here. There is log, but that log is a bit more complicated. The complex logarithm is, mm, yeah, it's not. I won't say complicated, but it is limited. It cannot be defined on all of C. Yeah. But that will take us in a different direction, so I will not say that. I should not say use the word complicated. I'm just saying that just use the word limit. If I say complicated, then everything is complicated in some sense. But then that's not how I want to say this. Yeah, but let's quickly get to the matter. Right. So it's better if I share the screen with you. You can see it for yourself. I have the book, but I don't have it in this room. Both the books. These are some books. Actually, these books have Indian publishers, so you should buy it. You should keep it with you. Okay, it's page number. Yeah, please try these problems. These is what you need to jog yourself with. Some Fourier analysis, but really slow. Right, and this is the chapter entire functions, but you need not worry about this chapter right now. Yeah, this is the what they talk about the gender. You can actually read this portion. This section 3 it doesn't require anything else from the book. I mean, it doesn't require much things. So you see, he writes it in a nice way, 1 plus n, and we say that this happens, and a useful necessary condition. So yeah, the way they write it, necessary condition that guarantees the existence, that I would call it a sufficient condition. Right? But that's Stein. We don't question him. Yeah. So by the way, if you know, Stein was the advisor of Terry Tao. He was the PhD advisor of Terry Tao, Elias Stein. Very himself a luminary figure in.
Yeah.
Yeah,
I was
yeah.
actually like just before joining class, I was reading about Stein,
Okay.
actually.
So here you are then. I hope this is the same Stein, and he has done a lot of big work in harmonic analysis. Hopefully someday you will study. Please keep in touch with physics. That will be very useful. Otherwise, you'll be like me, just manipulating symbols. So this summation an is less than infinity, then the product is converges. This is precisely the criteria I talked about, right? I wrote it in a different way, but it's the same thing. If you think about it, I didn't say anything different, right? Yeah, it's the same thing, right? At least if you look at the second. But you can read all this if you want. Yeah, because now because we are in complex numbers, you may have to in the end go into some complex analysis, but fine, for reals you know it, so it's not a big matter. But yeah, here is the deal. Here's the deal. This is what I was trying to write. So if Fn is a sequence of holomorphic functions on open sets, so the holomorphic you can forget. This, if you don't know, you can forget it. Open set, this is just what I wrote C. They are generalizing it to an open set. If there exists some constant Cn such that this happens, okay, such that this happens. So where am I wrong then in my condition? Yeah. So I wrote 1 second. Yeah, this is a stronger condition, right? So I'll just tell you what this is compared to my thing. So what I wrote is this, right? Okay, but they are directly applying the M test and saying it. Okay, but then the point is just that they are saying that uh, yeah. So 1 minute. Okay, so if this thing is less than ck, I mean less than, now this means for all z, right? Because its function is less, so it's again in the sup norm. Okay, so another in uniform convergence sup norm. This is this if this is true, if this is true and this is true, then that certainly implies this. Correct? It's just tautology. Right. It will converge uniformly then. That is exactly the Weierstrass M test. Otherwise, you could just prove it yourself. Okay. This is finite and this summation, sorry, is finite. Okay, this is less means is less than less for all functions. This is the numbers. Then that will imply this that you prove. That's the M test. Look at the M test if you don't know and prove this. Okay. They are saying that then this will product will converge uniformly. Okay, they are saying much other things, but yeah. Okay, but what I am claiming is slightly is a generalization of that because I'm not assuming that much. Okay, I am directly saying this, right? So my result will imply their result if my result is true. Okay, so try to prove it. I think it will be true, but yeah, there are several upshots to this. There are several interesting consequences of this, but unfortunately, we cannot get into them. Okay, maybe we do some complex. Like for example, if you look at this thing, so now you assume that the product converges. Okay, then you look at this is your favorite identity, right? In differentiation, right? When you take differentiation of product of functions, finite. When you take differentiation of finite products, no, it's like a favorite identity, right? You break a polynomial factor. When you differentiate it, you get x minus a1 by or whatever. Uh, I mean, not x minus a1, 1 by x minus a1 plus 1 by x minus a2, right? Plus 1 by, right, p
Yes,
dashed by
it
p.
has this it not this exactly, but a similar stuff has come in like ISI
Yeah,
instances
it keeps,
about polynomial.
yes, exactly, right. So that's those kind of things come, right? And so there's nothing special about polynomials. You can replace them by finitely many functions. And same kind of identity you will get. So you know this identity of finitely many functions. But when the product converges under these conditions, okay, then this happens for infinite sums, infinite products also is true. And that is a remarkable, that's a nice, I would say remarkable, that's a nice consequence. And then there are several big applications to these things. Read all this if you want to. Yeah, I mean, I can talk about these things if you're interested sometime. So we'll stop here. So let's meet on the other side, solve few, maybe at least two more questions. And but please, okay, maybe I will keep the screen and you can if it's note down the problems if needed and let the meeting end and then join after some time. Okay. Yeah, but try them and it'll be good. Infinite products, you can just read from there or you can just Google and read anywhere if you want. As I said, is there an apostle? That's a nice thing. Or you can just read it online. I mean, so like I I suppose like Kagsor's book also will have nice problems on infinite products. You can look at that and tell me some of them. I don't know that much about the nuances. I just know the general thing, which is good enough for those theory, complex analysis.